Mm. You're doing okay.
Were you guys hearing me or no? Probably not. I just muted you all so you can't answer. Anyways. It's one of those tricks. When the dentist asks you a question, it's like, I can't answer you. And you know that because you're in my mouth. But anyways, the law of cosines, just kind of quickly reiterate. So we've got the side angle side situation, or if we have the side 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 situation. So there's no angles, but we know the lengths of all three sides. Side, side, side. The lengths of all sides are known, but no angles are given. Also, so here we use the law of cosines to solve triangles in the side angle side and the side 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 cases. Okay. What you'll end up having is you'll have a triangle, and I think as a rule of thumb, try to use the law of sines. But if you don't have enough information, right, then you know to use the law of cosines, right? And so you don't need to remember what type of angle goes with which, right? You'll be able to look at your information that you have, and if you can't use the law of sines, then you'll be able to use the law of cosines, right? And so we've got theorem 12.4 here is the law of cosines, and you've got it on your handout. There, put it here. Do you guys have the chapter 12 handout? I only have one, but I can grab a photocopy. But here. If you use these ones for now, I'll grab your photocopy. Okay, so we've got the law of cosines, which says that, okay, well, if we've got a triangle with angle side opposite pairs alpha A, beta B, and gamma C, right, same as before, then we can use any one of these equations to solve for unknown values, right? Remember, kind of the easiest one to think about is the side, side, side case, right? Where we know all three sides, A, B, C, but we don't know any of the angles, right? So here we're solving for, we've got A, B, C, right? And we're able to solve for alpha. Here we're able to solve for beta, and here we're able to solve for gamma. Or if you prefer to have them rearranged, these are the same equations, just rearranged, solving for cos alpha, cos beta, and cos gamma. Right. Hence the law of cosines, because it uses cosines. Ta-da. Okay, great. Let's do an example. If we have to solve the following triangles, solve the following triangles. Give exact answers, which is fine, right? Because your calculator just gives you exact answers. Give exact answers and decimal approximations. And I'm going to say rounded to hundreds. and sketch the triangle. Just rough idea. So here, first one we're going to do is we're given beta is 50 degrees, A is 7 units, it doesn't matter, and C is 2 units. Is it too bright in here to see on the board? Is it okay? There's a spot right here for you. Yeah, I've heard that before. All right, so now, right, we've got beta, and the side opposite beta is B, right? And we've got A and C, so we have this side angle side situation. But also, if you tried to use the law of sines, right, the law of sine requires at least one angle side opposite pair, which we don't have, right? We have to have at least alpha and A, or beta and B, or gamma and C, right? But we don't have any of those. So we have to use the law of cosines, right? So it's not going to be a memory game. It's just going to be, oh, try the law of sines. That didn't work. I'm going to use the law of cosines. Okay? So with no angle side opposite pair, with no angle side opposite pair, to use for the law of sines, we apply the law of cosines. So we've got, we can solve for the side, right? The side that's missing. Solving for sides, I find, is a little bit more work than solving for angles typically, right? Especially if we're given 2 angles, then finding the third angle is really easy, right? Just subtract them both from 180. So let's solve for B. Now, it doesn't actually matter which order you do these. So we're going to solve for B, which uses B squared, right? Just using the law of cosines that we have here. If we're solving for B, then we may as well use the B squared equals whatever. B squared equals A squared plus C squared minus 2AC cos beta. Right, we have all those pieces of information, so we're able to solve for B. Well, B squared and then solve for B. So A was 7, so we've got 7 squared plus C is 2 squared minus 2 times A, which is 7, and C, which is 2, and then cos of 50 degrees. Right. Make sure you're in degree mode if you're using degrees as your angles. But besides that, you're off to the races. I'm going to start by figuring out the 2AC cos beta situation, and then I can subtract it from 7 squared and 2 squared. Cos of, make sure you're in degree mode, and it'll just say, especially if you're on this calculator, but most calculators will tell you what mode you're in. Up at the top, it'll have DRG, right? And it'll just highlight whichever mode you're in. It's really tiny, but I'm in degree mode, so I'm good to go. So I've got the cos of 50 times 2 times 7 times 2. And so I've got 49 plus 4 minus 17.99805,307. Keeping all those decimal places, of course. In fact, I'm just going to use it in my calculator here. And so I'll do brackets 49 plus 4, and then subtract the previous answer. So now I get 35.00194693. Remember though, that this is b squared, right? So we have to take the square root of this to solve for b. So b squared, b squared, b squared. B is the square root of all this, 35.00194693. So square root that previous answer. B is roughly, I didn't get the exact answer, but I'll show you what it is in a second here. 5.916244326. Notice that your calculator didn't give you the exact answer, right? And it's because it has the cos of 50 in there, and so it doesn't like that. And so this as an exact answer, right? Or B is just 49 plus 4, which is 53, minus 2 times 7 times 2 is what? 28 cos 50. Right. This would be your exact answer. But because I kind of solved it first, I've got that approximation. On the final exam, I'm not going to ask for the exact answer, only because I know some of the calculators are doing it and some of them aren't, right? So I will just ask for the approximation, but it's good to know what the exact answer would look like. Any questions about solving for B before we move on to alpha and gamma? No, because I asked for hundreds. So we are going to round it to beta is approximately 5.92. Because I've got the rounded answer and I told you to round to hundredths, for example, in the rest of your work, you're going to use 5.92, just remembering that that's an approximation, right? And so it's going to give us slightly tweaked results, right, but not too bad. Okay. After this, right, there's lots of ways that we could figure out the other two angles, right, alpha and gamma. One thing that we might notice is that, okay, well, if I have B and if I have beta, then I could just switch back to the law of sines, which I'm going to do just to practice the law of sines today. But you could absolutely just keep going with the law of cosines, right, using the cos of alpha or the cos of gamma, right, to solve for alpha and gamma. But we'll do problems like that soon as well, so you'll get to do it all. There are many ways. Oh, there's a page break actually. There are many ways we could proceed. But since we now have an angle side opposite pair, an angle side opposite pair, beta B, we can apply the law of sines. the law of sines. Just to get familiar with, you know, the smallest angles are going to be matched with which sides, right? The smallest angle is going to be matched with the shortest side, right? Or it's going to be opposite the shortest side. And then the biggest angle is going to be matched to the longest side, right? And because we have the lengths of all these sides, just as an exercise, let's just use the shortest side to find the smallest angle, which we already know, right? If the lengths are 5.92, 2, and 7, right, then C is our shortest side, and so gamma is going to be our smallest angle. And so just to get some we will start by finding the smallest unknown angle, by finding the smallest unknown angle, which will always be acute, right? It's always going to be less than 90 degrees because it's always the smallest, right? And so we can have one obtuse angle, but that's it. Right? Which will always be acute, right? And the smallest angle is the angle opposite the shortest side. The smallest angle is the angle opposite the shortest side. Okay. In this case, C equals 2 is our shortest side. So we start by solving for gamma. Oops. And remember, that was a really sloppy gamma. There. So if we're using the law of sines, right, then we use that sine alpha over A is the same as sine beta over B, and which is the same as sine gamma over C, right? So if we know beta and B, right, as our angle side pairs, then we can say that, okay, well, sine beta over B must be the same as sine gamma over C. Even though we solved for B, right? But sometimes there's nothing we can do about that. Remember, we said as much as we can, we're going to use angles that were given in the problem, angles and sides that were given to us in the problem as often as we possibly can. Sometimes it's not possible, right? We have to use something that wasn't given. In this case, we could if we use the law of cosines, right? But we're practicing the law of sines just kind of as a review from last day. So the sine of 50 degrees over B, which was 5.92, right? You're going to use your rounded value once you've left that Once you've given me the rounded value, right, that's the value that you can keep using. Of course, it's not wrong if you didn't, but usually people like to round stuff and forget about it. Sine of gamma over c, which is 2. Rearranging this, right, multiplying the 2 over to the sine 50 and the 5.92 over to the sine of gamma, and then solving for the sine of gamma, right, we get the sine of gamma is multiply 2 sine 50 divided by 5.92. Right. Doing our usual kind of switcheroo and solve. Right. Okay. Sine of gamma, now we can just plug in our values, right, is 2 times the sine of 50 degrees, right? Make sure you wouldn't have changed from degree mode, but just always make sure. And then divide that by 5.92. So we get is roughly 0.2587987994. Even if it came out to a precise number, because I use the approximation for B, right, it would still be an approximation. So now solving for gamma, right, we've got, oops, the inverse sine of 0.258798794. So keep all your decimal places in your calculator and then shift sine inverse. Previous answer equals, and I get gamma is approximately 14.99879903. So to hundredths, we round this to an even 15 degrees. .00 degrees. Now, if we know beta and we know gamma, we can solve for alpha, right? Because they all have to add up to 180 degrees. And so we've got, so we can solve for alpha, right? Because 180 degrees has to be equal to alpha plus beta plus gamma. And so alpha is 180 degrees minus beta minus gamma. 180 degrees minus 50 minus 15. So 180 minus 50 minus 15. Get 115 degrees. And now we've solved the triangle, right? Because we know what alpha is, we know what A is, we know what beta is, we know what B is, we know what gamma is, we know what C is. We've solved the triangle. So that's the end of that. Let's do another one, part B. What? That was just one question. I know. What if you only have sides? So A is 4, B is 7, and C is 5. Oh, I forgot to sketch it, didn't I? Ha. Stay tuned. just a rough sketch. So I know my alpha is 115 degrees. Let's do something like this. So I'm going to let this be alpha is approximately 115 degrees. Because I know that's my biggest angle, right? So I'm just going to start there, which means that A was 7. And then I'll arbitrarily place beta and gamma. They're not that different, right? And so I'll just put my, I don't know, gamma here. Gamma is approximately, what was it, 15 degrees. And C, we were given was 2, which makes this my beta, which we were given was 50 degrees. And B, we solved as approximately 5.92. Make a note in here. Okay. Any questions about that one before we go on to the side situation? No? All right. There's lots of ways that we could go about this again, right? We have these 3 sides, and so we can't use the law of sines, right? Because we don't have an angle side opposite pair, right? But we've got lots of options. We could solve for alpha, we could solve for beta, or we could solve for gamma. It doesn't matter. But just to mix it up a little bit, how about we solve for the largest angle, which means we're solving for the angle opposite the largest side, or the longest side, right? Which means we're solving for beta, because that's opposite side B. Just as an exercise, right? Get the largest angle out of the way, and then we can focus on the smaller angles. So we will start by finding the largest angle. And then I'll put in brackets, this will be an obtuse angle, right? If there is one in this triangle, right? So it's going to be larger than 90 degrees if there is one. So this will give us the obtuse angle if there is one. A triangle can't have more than one obtuse angle, right? And so if we've got the one obtuse angle, then we can kind of figure out what the other 2 might be, right? Because they have to be acute. The largest angle will be opposite the longest side. So in this case, we will solve for beta, right? Since it is opposite B, which is 7. If we're solving for B, right, you could use, let's see if it's still here, from the law of cosines, right? I'll delete this in a bit, but just so we've got it here. You could just use the original equations up top, right? That's fine. The next line is just, it's been solved for alpha, beta, and gamma, right? So if we're solving for beta, then, I don't know, let's just go ahead and use the cos beta as a squared plus c squared minus b squared over 2ac, right? Or you could just use the one with beta, so b squared equals a squared plus c squared minus 2ac cos beta, and solve for cos beta, but we don't need to because it's already given to us. But the reason I mention that is because you might run out of room on your formula sheet for the final, right? And so remember, you're making your own formula sheet, same idea, right? Exact same thing. You should have a pretty solid formula sheet by now, right? And so one page, you're allowed to use both sides, write whatever you want on it. And so if you're running out of space, right, you really only need these guys, right? And then you can solve for these. You don't need these on there. It's just if you have space. But you should probably have the law of sines and cosines on there. Even on this formula sheet that I gave you, important formulas for trig, right? There's the law of cosines kind of summarized down here. They use capital A, B, C, which we've used for the vertex, the vertices, for the angles, but you'll be able to decipher it. Okay, so it is kind of summarized on that handout as well if you want to steal from there. All right, so we're going to use the cos beta is a squared plus c squared minus b squared over 2ac. So I'm going to delete this and say, okay, well, cos beta is a squared plus c squared minus b squared. You don't want to get carried away and use, well, addition all the way across over 2ac. A is 4, so we've got 4 squared, plus c is 5 squared, minus b is 7 squared over 2 times 4 times 5. Four squared plus 5 squared minus 7 squared puts us at -8 over 2 times 4 times 5 is 40. Which, if we simplify, is -1 over 5. You don't have to simplify it because we're going to take the inverse cos anyways. So then beta is the inverse cosine of -1 over 5. So if we do -1 over 5 first, and then the inverse cos of that, I get beta is roughly 101.536959. To hundredths, beta is roughly 101.54 degrees. Okay. So now, again, we've got options, right, for what we want to solve for. We could use the law of sines, right, because we know beta and we know b, right? So we've got that angle side opposite pair. But if we use the law of cosines, right, we can keep using just the given information. And so that's what I'm going to do. We could use the law of sines now. But But using the law of cosines lets us use only given information. Whereas I think before, if you had a look, I think we had to use a solved one. I'm not 100% sure, but I wanted to practice the law of sines anyway. So here we go. Now we're going to stick to the law of cosines. So we could use the law of cosines, and if you did, that'd be totally fine. But using the law of sines, cosines, that would be confusing. Lets us use only given information. Which means that we're just going to solve for alpha and gamma, just using the cos alpha formula and the cos gamma formula, same way that we did for beta, to solve for these guys. So we can start with, well, it doesn't really matter, but I've got cos gamma on here, so why not do that? Cos gamma, from your law of cosines, you've got a squared plus b squared minus c squared over 2ab. A is 4, so we've got 4 squared, plus b is 7 squared, minus c, which is 5 squared, over 2 times 4 times 7. Which, if you do the math, it's 40 over 56, which, if you want to simplify, is 5 over 7. I think your calculator just does it, actually. Yeah, it just gives you 5 over 7. So now, if we're solving, so this is cos gamma all the way along here. So now if we're solving for gamma, we take the inverse cosine of 5 over 7. So the inverse cosine of 5 over 7, I get gamma is roughly equal to 44.4153086. To hundredths, gamma is going to be 44.42 degrees. Let's do it all over again with cos alpha. Same idea. Remember, you could say, okay, well, now I know beta and I know gamma, so I could solve for alpha, right? But we solved for beta and gamma. So for me, I would recommend just solving for alpha using cos alpha, and then check that your answers make sense by making sure that they add up to, we'll see, roughly 180, right? Because we've been rounding, right? And so that's going to be a better check to have than to rely on it to solve for alpha. And so I'm going to solve for, so cos alpha from your theorem is b squared plus c squared minus a squared over 2bc, which is going to be 7 squared plus 5 squared minus 4 squared over 2 times 7 times 5, which is 58 over 70. And this is cos of alpha all the way along here. And so solving for alpha, we've got the inverse cosine of 58 over 70. So alpha is approximately the inverse cosine of 58 divided by 70, 34.0477 3237. So to hundredths, alpha is approximately 34.05 degrees. I'm not sure if I put degrees. Yeah. So now, if we have to sketch this out, right, our angles kind of tell us the shape of this thing. So we've got a 34 degrees, we've got 44 degrees, and 101 degrees. So again, beta is my largest angle. So I'm going to start there and just kind of plug my way. The difference between an angle of 44 and 34, I mean, if we're sketching it, it doesn't really matter. So I'm just going to do kind of a beta is approximately 101 point, is it 54? Yeah, 0.54 degrees, which means that B is on the other side, and B we were given was 7. And let's make this angle our smaller angle, which is alpha, which is roughly 34.05 degrees, making this side equal to A, which is 4. And then gamma is roughly 44.42 degrees. So C, which we were given, is 5. Because the lengths of A and C are roughly, they're very similar, 4 and 5, right? We expect those angles to also be very similar, right? If we do 101.54 plus 44.42 plus 34.05, oops, I get 180.01, right? The reason for that is because I've been rounding, right? And so we have to keep that in mind. But as long as our answer, right, our total angles have to add to 180, and then if we can convince ourselves that that 0.01 is just due to rounding, right, because I was rounding, then we know we've got the right angles, right, or the correct angles. Notice that using the approximations, right, alpha plus beta plus gamma is equal to 180.01 degrees, which is geometrically impossible another which is why it's important, right, to show that these are just approximations, which is why it is important to show that these are approximations, to show that these are approximations. So let's do example 12.2.2, which is on your handout. It looks like a big problem, but it's actually not. So we've got this problem. So a researcher wishes to determine the width of a vernal pond as drawn below. From point P, he finds the distance to the easternmost point on the pond to be 950 feet, so that's labeled, while the distance to the westernmost point of the pond from P is 1,000 feet. If the angle between the two lines of sight is 60 degrees, find the width of the pond, right? Of course, if you know two distances, right, so two sides and an angle, we have to use the law of cosines. But besides that, it's not really that bad, because what do we want to solve for? We want to solve for this distance, oops, from here to here. Arbitrarily labeling this as alpha is 60 degrees, then A is going to be that distance. You could have used beta or gamma, it doesn't matter. Right. Then these two angles, again, just kind of picking whatever works. Let this be gamma and this be beta. Then we know, right, that B is going to be 95 feet and C is going to be the 1,000 feet because it's opposite gamma, right? So the only reason I labeled those, right, is to be able to see which formula I can use, right? Because then I can kind of say, okay, well, if I know B and I know C and I know alpha, I'll be able to solve for A. Right. But you could have labeled these, as long as you used your pairs correctly, it doesn't matter how you label these. So if I want to solve for A, then I can use A squared is B squared plus C squared minus 2BC cos alpha. Right? That uses all the information that I have, and it's just from the law of cosines. So in this case, we said B is 950 feet. Oops. But I'll just use 950 for now. 950 squared plus 1,000 squared minus 2 times B, which is 950, times C, which is 1,000, times the cos of alpha, which is 60 degrees. Making sure you're in degree mode for 60 degrees. I get 950 squared, I'll start there, plus 1902500 minus, and I'm going to simplify the 2 times 950 times 1,000, just so I have something clean to work with here. 2 times 950 times 1,000 is 190, 1, 2, 3, 4 more zeros, 1, 2, 3, 4, cos of 60 degrees. Cos of 60 degrees is 1/2, but even if you just use your calculator, right, you would find that you would have 1902500 minus cos of 60 times 190, 1, 2, 3, 4. So I've got 950,000 even. Only because cos of 60 works out to 1/2, which is a nice number to work with, typically. So 1902500 minus 951234 zeros. I get 952500. Remembering that that's equal to A squared. Right, we've got A squared all along here. Solving for A, right, we have to take the square root of 95 952,500. Oops, I almost squared it. The exact answer is 50 root 381. But of course, that doesn't really tell us. If you told someone, oh, it's only 50 root 381 feet away, it's not very good. So we use an approximation, and so, which is approximately 975.9610648, or to 2 decimal places, 975.96 feet. If I don't tell you what decimal places to round to, right, the default, let's say, is 2 decimal places, right, just so you have a kind of a go-to. It's usually pretty safe. Any questions about that one? No? So just like before with the law of sines, we're going to look at how we find the area of a triangle kind of matched to the law of cosines, but also it just works for any of the two. I didn't have time to work through the proof, but they're definitely related. You can tell because there's 1/2 in there, and the sine in the other one would convert to the length of a side. So anyways, I digress. As long as we know the length of all 3 sides, we can find the angle of the area of a triangle using Heron's formula. To find the area, there we go, the area of a triangle, given or knowing, right? Knowing means that you've solved it, or if I've given it to you, given or knowing the lengths of all 3 sides, we can use Heron's formula. Which is actually named after Hero of Alexandria. Kind of an interesting guy. I went down a Wikipedia rabbit hole, but pretty fun. Because there was a link in the textbook that said, oh, also known as Hero's formula, because his name is actually Hero. And so somehow, I guess with the Greek letters, anyways, it translates to hero or Heron. And so we use Heron's formula, but you could also call it Hero's formula. Just a little fun fact, an LFF, if you will. A little fun fact. So we've got Heron's formula on your handout. Which just says, suppose A, B, and C denote the lengths of the 3 sides of a triangle, right? Any triangle. Let S be the semi-perimeter of the triangle. So the semi-perimeter is just the half of the perimeter. If you had to find the length of the perimeter, it would be A plus B plus C, right? Semi of that, half of that is 1/2 A plus B plus C. Then the area A enclosed by the triangle is given by the square root of S, which is the semi-perimeter, times S minus A times S minus B times S minus C. I'm sure you could work it backwards to find that, that other area formula. But in general, as long as you know the lengths of all 3 sides, you can just use this formula. So, which is pretty cool. Example. find the area enclosed by the triangle that we just worked with. Not recent, not the most recent, but just previously. Find the area enclosed by the triangle A is 4, I'll just say units, B is 7 units, and C is 5 units. So I think you've noticed on that last assignment that I gave you, right, it just asks, so you have to solve the triangle and then you have to find the area, right? And so you can find the area using either of the formulas. So first thing I'm gonna do to use Heron's formula is I'm gonna find S, the semi-perimeter. Find S, which is 1/2 of A plus B plus C. Heron's formula is also on an old handout that I gave you, right, that one that I copied out. This one, right? Heron's formula is on here if you wanted to steal it from that. So S is 1/2 and A is 4 plus B is 7 plus C is 5. And so S is going to be 8. Kind of cut to the chase. So now that we know S, right, now we can use Heron's formula that just uses S, A, B, and C. So A is the square root of S times S minus A times S minus B times S minus C. So A then must be the square root of 8 times 8 minus A, which is 4, times 8 minus B, which is 7, times 8 minus C, which is 5. So A is the square root of 8 times 4 times 1 times 3, which is the square root of 96. Which, if you do the square root of 96 on your calculator, it'll just give you A is 4 root 6. As an approximation, we get A is approximately 9.79795891. If we're rounding to 2 decimal places, A is approximately 9.80 units squared. Because it's an area. How does that feel? That's the end of it. What? So we have officially covered all the material that you can expect to see in this course. I sense that you have better places to be with your presentations, and so we'll do our final exam review on Thursday. Make sure you've handed in your assignment 8, and if you don't have assignment 9 yet, come grab it, and I'll see you guys on Thursday, and good luck on your presentations. I stopped printing enough for everyone. Oh, is that the... Oh. Great. Bye, guys.